Hopefully now we can start, and hopefully the audio will be better this time. Okay. Hello. Okay, this is not too loud. Maybe I should put this here instead, so it's a little bit further from my face. Beautiful. Okay, we are. What did we talk about last time? We're going to talk about. Once again, we're going to do a review of things that this time you actually know, because this is going to be a review of. What we actually did last time, and then we're going to prove a very new and interesting theorem, which is central to a lot of the quantum mechanics that you do anywhere. And then after today, we'll hopefully be able to, finally start reading and learning about what quantum mechanics is. And I will hopefully assign a few readings for the first time in this reading group, which will actually be about quantum mechanics. So we have 1, 2, 3, 4, 5, 6 people. I need to know this for attendance purposes. I will log that later. Okay. So let's start with some of the things that we talked about last time. So one of the things that we defined last time we talked about an inner product, right? So I will not actually write the definition, but okay, we spoke of inner product spaces. Okay, and the inner product is some function. You have a vector space and you have some function which has two inputs, and it outputs some complex or real number. And I'd say for our purposes, always outputs a complex or real number. In quantum mechanics, you'll always deal with complex numbers. But okay, the real case is also quite important. But that's fine. So, okay, that's good. And so the real definition that we had, that I will define, so this was some function with some properties. The real thing that we defined were orthogonal vectors. So let V be an inner product space. Then U and V, vectors U and V, are orthogonal. If U inner product V is equal to 0, right? So this was how we defined two vectors to be orthogonal, and this is very similar to the dot product, right? You may remember from high school math or something that if you have two vectors in R2 and they are orthogonal, then if you were to take the dot product, meaning you multiply the components, the x component of this vector with the x component of this vector, and then add all of that up, that if these two vectors are in fact orthogonal, that you will get 0 if they're perpendicular to each other. And this is a kind of statement about like total linear independence. Like if vectors are orthogonal, it's almost like they're completely linearly independent from each other, and don't have anything to do with each other. Now, ideally, this very vague statement that I just made, ideally we can put it in some sort of theorem. And okay, let's write down some theorem. I'm not sure if this theorem in fact captures exactly what I just said, but let's write down the following theorem. So theorem. Let E1 up to EK be orthonormal vectors. So orthonormal vectors means that any two of these vectors are orthogonal to each other, and if you compute their norm, then you get 1. So let's recall that the norm was some function which took in a vector, gave back a real number, and this function was given via, for us, v gets sent to the square root of v inner product v. Yes, so this is something that people hopefully remember. This is how we define a norm on our vector space. If it has an inner product, then you can define the concept of a length of a vector. Right? Length of a vector is given by v being sent to the square root of the inner product of v with v. Yes?
Is that the same definition of the norm we use in quantum mechanics?
Yes, this will be.
Just in general, are we going to assume that's
well, look,
what
this is a
norm
norm. This is a norm that comes from an inner product space, right?
Yes.
So usually a norm, you define a norm to be any function on a vector space which satisfies like 3 properties, right? You have triangle inequality, you have positivity, you want it to be 0 if and only if the vector is 0, and you also want to be able to pull out factors of lambda, or absolute values of factors of lambda. So that's what you usually define a norm to be. But in the case of an inner product space, you have this very convenient norm that comes from the product, from the inner product structure, right? It immediately induces a norm, and so we will almost always use this to be the norm of vectors, like entirely always. I can't immediately think of an example where we wouldn't do this. For operators, we wouldn't do this, but well, because this wouldn't be defined for operators. But yes, so. As far as we're concerned, the norm that we use is always the one defined by an inner product. But the idea is that you could have a vector space that doesn't have an inner product on it, but it does have a norm defined on it, right? Technically, you don't need an inner product to define a norm, but in this case, we do. Okay, good question. So, theorem. Let E1 to Ek be orthonormal vectors. So the inner, meaning that, so IE, EI, EJ is equal to 0 for all I not equal to j, and EI, EI is equal to 1. So this is given. This is just what orthonormal means. Can people see the yellow? Is that fine as a color? Okay. Now, so let V be in the span of these vectors. Right, so we kind of take these orthonormal vectors, make some minimal vector space that creates all of them, and look at a vector in the vector space, in the minimal vector space generated by E1 through Ek. Right, remember that the span is kind of the smallest vector space that includes E1, E2, E3, and Ek. Yes? But okay, so then just kind of by definition of what span is, I should be able to write V as some sum of AI, EI from 1 to K. Right? So it should be some linear combination of the EIs, right? So far I haven't really given a statement of the theorem yet. I just kind of told you fun facts. Okay, sorry. I can actually move my laptop because the only thing that matters is the camera. So I can remove my laptop almost completely. I am definitely convinced that none of this will fall down on me. Okay. Okay, you still have to look through the camera, but that's okay. Okay, so far I haven't really given you any statement that we are, so far all of this is obvious. Yes, I just defined what things are. Okay, now the statement of the theorem. So the statement is that the AI are going to be given by V inner product EI. So this is the statement of the theorem. So it implies that AI is equal to V inner product EI. Right. So in some sense, we can use if we have an orthonormal basis, then we can use the inner product to directly figure out what the coordinates are in some orthonormal basis. Okay, and I think we proved this theorem last time. Do people remember if we proved this theorem last time?
I think we did.
We did. So let's prove it again.
Yay.
It's not a difficult theorem because really all you need to do is just computation. I don't know, so does anyone actually watch any of the videos? When I write on this board, is it like at all visible?
Yeah, I did turn
Okay.
the camera on.
Oh, if I turn, oh, okay, right. So all the times where I didn't turn the camera and it wasn't visible, I see. That's where I went wrong. Okay, thank you. All right. So let's maybe even move it a little bit further. Oh, well, you can't do that. Okay. Okay, this is maybe not the best.
Why don't we put the laptop on one of these?
No, that's true. But then the problem is it was blocking the view for people.
I mean, like these things.
Oh, on those things. Okay. That's like I've already wasted enough time with all these setups, so I want to kind of move on. Okay. Okay. Now, hopefully, people can still see. Okay. So, proof. Okay. So, we're trying to show that if you have this expansion, AI is equal to V inner product EI. How do we do this? Let's just, compute this side explicitly and, get that it's equal to this side. This is a very straightforward computation. So let's try and do it. And if it's not straightforward, you should stop and ask. Because if it's not straightforward, that means you're missing something. Okay, so we want to compute V inner product EI. Do you agree? Okay. Well, what do we know that V has to be? Right, we just, we assume that V is what?
In the span of
Up to EK, yes. So this means that I can replace V with,
sum of AI.
Yes.
and,
yes, the sum. So its expansion in the E1 to, EK basis. So this is K, AI, EI, and, oh, well, I shouldn't be using, I made the same mistake last time. Let's use J as the index for addition, and EI to be this. All right. This is good. Okay, now, what do we know about the inner product?
the first entry.
Yes, okay, it's linear in the first entry. So what can I do?
Take out the sum
Yes,
from
and
this thing.
I can take out the sum from this component, and what else can I do? It's linear, so linear has two conditions. One is the addition one, and then the other one is?
You can also take out the AJ.
Yes, I can take out the AJs. Correct. So I can, do the sum of AJs, AJs, inner product EJ, EI. And this is I equals 1 to K. Do you agree? Makes sense. Now, so these AJs, we don't know what they are. Yes?
Is this I or a J index?
J, yes, there should be J. The sum's over J, sorry. Okay. Now, what do we know about the EIs and EJs? Pardon? They're orthonormal, yes. So, EJ and EI is what? EJ inner product EI is what?
0 except for the one which is 1 when that's it.
Exactly. So all of these terms in the sum are 0, except for the term where j equals I, right? So in this case, this sum has to just reduce to AI times the inner product of EI with EI. Do you agree? Because all the other terms are just 0. Yes? Okay, but we assume that these vectors are orthogonal, but they're also normal. And since they're orthonormal, EI inner product EI has to be Exactly. So AI. Good, okay, and so we kind of proved the theorem. Okay? And so now we can really think of it in this way. If V is in the span of E1 up to EK, where these guys are orthonormal, so orthonormal, then I can write down the following expansion, that this implies that V is equal to the sum, so well, let's not even write the sum, let's write V E1 1 plus V E2 2, and so on and so forth. V K EK. Do you agree? Okay. And so this is a fairly important statement, even though it's a really easy one, and we're going to use it extensively now. Right, so remember what I said before is that this is kind of a statement about the E1s and the EKs all being kind of completely linearly independent, right? All the coefficients in the expansion of V, it's V inner product with E1, right? And this is, you can kind of read this as V inner product E1 is like, it tells you how much of E1 there is in V. And this expansion only works, right, from this derivation that we did, only because EI and EJ are completely orthogonal to each other, right? They don't share anything in between them. Yes, which is the only case where you can do such a nice decomposition. Right? So this is a common mistake people avoid. They kind of think, oh, if I had any basis, right, then I have this kind of decomposition. No, you don't. Computer, of course, turned off. Let me actually, let me make it so it doesn't turn off ever. Screen blank turns the screen after a period of inactivity. It actually says that it never turns it off. This is strange. Okay, that's fine. Okay. All right. Is this good for people? Yes. Okay. Okay. Now, so I will kind of erase all of this, rewrite it slightly more neatly, and we will have finally a new definition. Okay, so UV are orthogonal if unit product equals 0. So definition, then we had theorem that EK be orthonormal and V's in their span. Then this implies that I'm just rewriting what I wrote there. Okay, good. And so I can now erase this proof because we don't really need it. It's hopefully straightforward. So now,
Wait, I have a question.
yes.
So was the definition of orthonormal the thing with if I is not equal to j, it's equal to 0?
The inner
And then-
product.
Yeah.
So
Or
a set of vectors is orthonormal if any two of the vectors are orthogonal to each other
oh,
and they all have norm 1.
okay.
Yes. So ortho which is the orthogonal part, and normal is the unit 1 norm.
But is that exactly equivalent to you writing that inner product of EI, EJ is equal to 0 and inner product
Yes,
of EI
so if all of them, if any two vectors are orthogonal, that means that their inner product is 0, right, by definition. And normal means, so their unit norm, their length is 1. So saying that the vectors are orthonormal is equivalent to saying that any EI, EJ is 0 and EI, EI is 1. That's, yes. Sorry if I wasn't clear. Okay. So now we give a definition. I'll write it in red then. So, definition. So we'll kind of restrict ourselves for now to finite dimensional vector spaces. And then, actually, let's not restrict ourselves to finite dimensional vectors. Let's just say something general. So let T v to w be a linear operator, linear map, where v, and I have this inner product subscript v, and w, inner product subscript w, are so inner product spaces. So I have two vector spaces, one is v, one is w, both of them have an inner product on them. And so I'm going to distinguish between the inner products on one vector space and another. I'll use like a little v subscript and a little w subscript. That makes sense? Okay. So then the definition is the adjoint map of T called T star is the map such that the following condition holds. The inner product of W TV, so this is the W inner product. So is equal to T star W V. It's in the V vector space, so T star goes from W to V. Okay, and so this is kind of the point of this definition. All right. This is maybe hard to see here. Okay, good. So let's stop and think about this for a second. So we're given two vector spaces and we're given a linear map between them. Right? And one of the natural, and so this should be true for all V and W. So for all, this is true for all W and W and V and V. Okay. So suppose we have a linear map, right, from V to W, and both of these vector spaces are inner product spaces, right? Maybe I actually shouldn't have started with this. I'm starting with the wrong thing. I forgot, but that's okay. And the idea is, if I take a vector in V, I apply the map to it, I get a vector in W, right? So I can take the inner product of TV with something else in W. That makes sense? Because, TV is something in W, so I can take something else, take the inner product of it. Okay. You take the inner product of TV with W. The idea is that the adjoint map is something that I can instead go the other way. I can define something that goes from W to V, and that if I applied it to the, W vector here, it would still kind of give me the same inner product as as W inner product TV would give me. But note that T star goes from W to V, it goes the opposite direction, right? So this is something that is kind of makes these operators play nicely with the inner product in W and in V. Right? So do people kind of see the definition here? So T star kind of goes the other direction, takes a vector from in W, sends it to a vector in V, and the point that we'd call a map to be the adjoint of T if it has this property, where it kind of works nicely with the way these inner products work. Yes? Do people see the definition? I'm maybe not explaining it too clearly, but do people see why to have this condition T star has to go from W to V and not the other way around? Okay. So there's a few clear questions that we want to be asking about this thing. So one of the questions that we want to ask, I feel like I'm not on camera that much because one of the questions that we want to ask is, first of all, so we define this T star thing. Well, does a T star even exist, right? So if I give you any linear map, can I find a T star that has this property? So that's the first question we want to ask. The second question we want to ask is this T star unique, right? Is it possible to have multiple maps that kind of go back from W to V and all have this property? Okay. And the other thing is, I said that T star is a map, right? It's not obvious that this has to be a linear map. That's the other question. Is T star even a linear map? So it turns out, of course T star is a linear map, and for the case of finite dimensional vector spaces, you always have a T star that has this property, and we're going to construct it explicitly. And one of the questions that we always ask is, suppose we have a map, right? What was as soon as we learned the concept of linear maps, what was the first thing I introduced right after? That's related to linear maps.
Wait, does T have to be isomorphic?
No. T can be any map, any linear map.
Then if you want T star to exist, shouldn't you need every W can be reached, and at least it has to be surjective?
No. It doesn't have to
But
be.
you said it should hold for all W and W.
Yeah.
Which means that there is at least some sort of T V that goes to W.
No, not necessarily. No, because W is some other vector that I just inner product with TV. Right?
Oh, okay.
It doesn't have to be hit by T.
Okay.
I can always take the inner product of one vector with another vector, because the inner product structure, that's something inherent to the vector space. It has nothing to do with the linear map itself. So back to good point though. So back to my question. What was the first thing that I introduced? After we said what a linear map is, what was the next thing that we said?
Matrix representation.
Exactly. We said that actually if you choose a basis in the original space and choose the basis in the target space, we were what's the matrix, right? And how do we write that down? So the fourth question, what are the three questions? The first question was, does a T star exist, right? Is it linear? Is the T star unique? And then the last question we're going to ask is, how does the matrix of T star relate to the matrix of T? Right? That's another reasonable question to ask. And it turns out that the answer will be fairly familiar, though it's going to be a little bit different. And there's a reason why the answer is fairly familiar, but I will not talk about that reason. Does anyone want to guess what the answer will be? How the matrix of T is associated to the matrix of T star?
If I see a transpose, I'm going to cry.
Yes, so it's going to be, in fact, the transpose. But there's one more thing. It's not just the transpose. So I'm going to tell you. So the matrix of T and T star is related by a transpose and something else. It's obvious in some sense that it has to be a transpose. Why? Because now, instead of going from V to W, we're going from W to V. So you need the dimensions to match. So you need to do a transpose, right? And then the other thing is, a transpose means that,
Oh,
everything's
wait,
perfectly linear.
wait. Oh no,
But
no.
this is linear in the first entry, but not the second entry. So what do you need to add? You need to conjugate, exactly. So it's going to be a conjugate transpose. And okay, we'll prove that in a moment, and we'll get to it. But for the people who know, it's kind of clear that it has to be, the matrices have to be related as a conjugate transpose, simply because this is linear, but this has a conjugate in it. So you need to have a conjugate somewhere, and you need to have a transpose because, well, I guess V to W, you have to flip the dimensions. Okay. But maybe that's just some random intuition of me saying words that aren't that meaningful. So, so before we do all of this, so this is what we're trying to do, right? So we have these adjoint operators, and we want to try and somehow characterize them. And then we're going to prove an important theorem called the spectral theorem about them, and that's kind of the punchline. But first, let's understand this. And to understand this, what are we going to do? First, let's understand in general, how does a matrix of a linear map look like in general? Like not even without the T star. Let's first understand what the matrix of T looks like. However, in an orthonormal basis, right? So this is what we're going to do now. So a corollary of this theorem. So corollary. So let E1 up to EM so be an orthonormal basis of V, and E1 tilde up to En tilde be an orthonormal. Maybe I should be writing this in a different color. Like yellow, let's say. Orthonormal. Okay, let me just rewrite it. Basis of W. So it's maybe confusing that I'm writing, both of these as like E's and E's with a tilde above it, but hopefully it will be clear. Computer didn't just randomly turn off. I think that would be really, really nice. But okay, because I want to use V and W for something else. Okay, so the statement is that the matrix, so let's call this basis alpha, and let's call this basis beta. So okay, the basis on V is alpha, basis on V is beta. So okay, the matrix going from alpha to beta of some linear map T. If we were to take this matrix and look at the ij entry, this has to be the inner product of T V J with not V. I want to be using E. Sorry, T E J with E I. So this is kind of the corollary of this theorem that we just proved. Why is this the case? Does anyone want to try and tell me why it's the case? So this is, I write down the matrix and I looked at the ith, jth component.
Why do you have like?
Oh, there should be a tilde over here. And this should be the inner product in W.
Why is the case?
Yes, so why does this follow from that theorem?
Because you wrote the matrix going from basis alpha to basis delta.
Yes. And the matrix in the matrix we define that to be the numbers of taking TEJ and expanding it in the target basis, right? So recall that I'm just asking you to like tell me the definition of a matrix again, essentially, right? So I said a matrix going from the basis alpha to the basis beta, the ith and jth entry, is what you would get if you took the jth basis vector in V, applied T to it, and expanded it in the beta basis, and looked at the coefficient in front of EI, right? Do you agree? So if we call these matrix elements Cij, then the idea is these matrix coefficients were defined such that Tej was equal to the sum of Cij EI. So right. So this is how these matrix coefficients were defined. They were just defined to be the coefficients of this expansion. Right? But Tej, right? That's just some vector. That's in the span of these orthonormal E tilde i's, right? And so in that case, I know that Cij has to be just the inner product of Tej with EI from that theorem. Do you agree? Okay. So, straightforward coding. Do people see how this follows? This is important. I want this to be very clear. Okay? Okay. So let's maybe copy it down in this little section here. Okay, we have lots of time. So the corollary was that the matrix element from alpha to beta, matrix element of T and of Tij was equal to T Ej, comma E I twiddle. And remember, this is the inner product in W. This is the inner product in the target space. Right? Okay. So, very good. Now, let's remember the questions. So, can I erase this? Okay. Should have maybe written all of these things on the top board so I could think that. Okay, that's fine. So, remember all the questions that we wanted to ask and answer. So, the questions. So, first of all, does T star exist? Question 1. Question 2, is T star unique? Question 3, is T star linear? Question 4, is, so what is the matrix from the beta basis to the alpha basis of T star? So these are the 4 questions that we want to answer. We will answer all of them in one go. All of them at once. Because I will explicitly construct to you T star, and from the construction it will be clear that it is linear. Hopefully it will be somewhat clear that it's unique, and we'll definitely be able to read off the matrix straight away. In fact, that's how we're going to try and define it. So first, we're going to say, suppose it was defined, what would it look like? And then realize that, we can just go backwards and define it that way. So kind of construction. So suppose the answer to all of the above was yes. And suppose we knew the answer. And then we're going to work backwards, okay? So suppose the answer was yes. Suppose the answer was yes. Do you agree? So let's answer the following question. What would T applied to EJ tilde B? What would T star applied to EJ tilde B? So what is this? What would this be? Apply previous theorem that we just had. No, not necessarily. That wouldn't necessarily be the case, no. So what would, this would be a vector, right? It would be some sum of vectors. And so just, you can use this formula, right, to compute it. So this would be what times E1?
Why can you use that formula?
Pardon?
Why can you use that formula?
This one?
Yeah, that's about. I'm confused. That's about the other map.
Okay. Now use the symbol T and replace the symbol it with the symbol T star, and swap alpha and beta. What changed? Right, T star, we're assuming is some kind of linear map for now, right? We don't know what it is. So you can just kind of say, oh, instead of calling it T star, call it whatever other letter you want, and just apply the same stuff.
Okay.
Right? Also, the other thing is TEJ is some vector in where?
It's in V.
Yes, it's in V. It's some vector in V. And so if it's some vector in V, then I should be able to just use this,
Okay.
right?
Yeah.
So that's where this came from.
Okay.
So TJ should be what? TE tilde EJ should be what? You should be reading this. So TJ should be what?
Like T star EJ.
Yeah, T star E tilde J.
Yeah, E tilde J.
It should be.
Should
What should it be equal to?
well, okay. On the left entry would be T star E tilde J, and then
Yes.
on the right it would just be
So
E.
E1 plus.
Yeah.
So the tilde will be here. So the other thing is, where is this inner product?
It's in the linear complex.
No, yes, but which inner product is this? Because we have two inner products, right?
Oh.
We have one on V and one on W. Is this the one on V or the one on W? This is the one on V. Yes, good. So plus dot 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 plus the inner product of T E tilde J with E I okay, plus a dot, plus dot dot dot. Plus the inner product of T E tilde J, inner product E, what's the index on the last E? M. M because now that we're going back from W to V, and V is an M-dimensional space. Oh, I erased what I wrote before. I'm sorry, so I said T is from V to M, V to W, and this one, I'm using the wrong color scheme here.
You dropped the stars on the T's. It's actually
Oh, true. Sorry, there's a star here, there's a star here. So T was from V to W, and V was E1 up to EM, and W was E1 tilde up to EN. Okay. So right now I'm saying, suppose all of these were true, right? Suppose all of these were true, how would this look like? All right? Now, what do I want to do? Well, I want to be clever. And I want to use this property, right, of the adjoint. I'm saying suppose the adjoint exists and everything works, even though we haven't proven it. So let's use this property of the adjoint, because this is really the only thing about the adjoint that makes it interesting. Right? So how can I do that? What can I do here? What can I do here? How can I use this property?
What are you trying to do again?
So I'm trying to somehow use this property and apply it to this formula.
Well, what are you trying to get out of that formula?
We're trying to find a way to figure out what this should be, right? Right now, we don't know if this is even defined. So we're saying, suppose it was, what will it look like? Then at the end, we're going to get an expression that we can actually explicitly compute, and then we can say, oh, let's just define this to be that final thing. And then we'll realize, oh, okay, then it's defined. That's what we're trying to do. So you'll see in a second. So how can I apply the defining property of T star to this combination? So for the people looking at it, that's the defining property of T star. Okay. How can I do this?
You replace all the inner products with E tilde J and T E whatever it makes.
TEI, yes,
TEI.
exactly.
And
So,
then you want
the whole point of the inner product was, of T star was that if I do T star on this side, I can instead do T on this side, and the inner product stays the same. But it just flips to an inner product in a different space. So let's rewrite this now. So this would be E tilde J, inner product, TE1, and then this inner product is now in W, E1. Am I doing this? Okay. So this is going to be E tilde J, TEI, W, EI, J, TEM, product, EM. Okay. Yes? People agree? And now, okay, so this was not something that was defined, right? Because we said, okay, suppose T star exists. Okay, but what if it doesn't? We don't know if it exists yet. That's what we're trying to prove. But now let's look at this line, right? Okay, at this line, all of these vectors, E1, EI, EM, whatever, all of these vectors, they just came from the vector space. They're just some orthonormal basis. We got it from the vector space. That's fine. Do you agree? So these vectors have nothing to do with the T star, right? Now, if we didn't know T star exists, but we knew what T was, these guys we can compute as well, no problem, right? This coefficient only depends on what TE1 is. But I said that we're given what TE1 is. Do you agree? Yes? So in fact, this whole line is defined independently of this whole definition only depends on what T is and what the bases are. And we know what that is. Do you agree? So now what you can do is you can say, okay, just define T star to be equal to this. Just define T star through the equation above. So the construction is, so that the punchline is define T star through equation above. Okay? Yes?
Are we in like V vector space since we have like m dimensions?
Yeah, so T star, so if T goes from V to W, then T star goes from W to V.
So we're gonna have m dimensions.
V is going to have M dimensions.
So we can change the coefficients, but it doesn't change the dimensions, right?
Oh, what do you mean?
Like coefficients.
Well, the coefficients,
The-
all I did, this coefficient should be equal to this one, right?
Yeah, yeah.
By the defining property.
Yeah.
So, yeah, so the number of coefficients is the same because the number of vectors is the same. Right? I'm maybe not sure what you're asking.
No, yeah.
Right? Makes sense. Okay. Good. So now what I'm saying is like erase this top line, just forget about it. Right? Just forget this top line and just define this to be that. Why can we do it? Because I said that, remember the thing I said about vector spaces is that, about linear maps is, the nice part about linear maps is to define how a linear map acts, all you have to do is define how it acts on the basis. Right? And that fully determines the linear map. Right? Instead of specifying how it acts on infinitely many points, for a linear map you can just define how it acts on the basis. And what did we do? We just defined how this map acts on the basis of W. Do you agree? So this equation fully defines this linear map. Yes? And now what I want to do, now I want to say, okay, if I was to define the linear map like this, does it satisfy all of these properties? Right? Okay, which one does it obviously satisfy? Well, 2. Which 2 does it obviously satisfy? Yes.
Existence, uniqueness.
No, I'm not sure about uniqueness. Uniqueness is maybe not obvious, but existence is obvious because I just defined it, so it exists. Cool. The next thing that's obvious is that it's linear, right? Why? Because if I define a map just by telling you how it acts on the basis, then you kind of automatically extend the definition by linearity, so you kind of just define it to be linear in a sense, right? Because if you just tell me how the map acts on the basis, then you just kind of assume, oh, I can expand anything on the basis and work that way. Okay, so from this definition, this is a check, this is a check. Okay, uniqueness. Let's check uniqueness. Actually, let's check uniqueness at the end. Even the uniqueness is easy, I want to kind of stick with this equation. Now, what we want to figure out is we want to figure out what is the matrix of T star in the beta to alpha basis, and ideally we want to express that in terms of the matrix of T in the alpha to beta basis. Okay? Yes? And so let's answer this question first. What is the matrix of T star? So, can I erase this? Do people remember this property? Yes? Okay. Well, not erase, but I mean, just move this to the side. Okay, so I will rewrite this again. So we defined it through this equation. We defined this to be as follows, to be I need to be using the other color. T1E1 plus dot dot plus dot dot TEI plus dot dot. Okay, and now let's fill in the rests. EJ tilde. EJ tilde. tilde. Okay. So from this definition, if you're asking me the question, what are the matrix elements? So question. What are the matrix elements going from the beta basis to the alpha basis of T star? Okay. So from the equation above, you should be able to simply just read off the answer. What's the answer? You should just look at the equation, look at it very carefully, and just read out loud what you see.
So just the like yellow inner product.
Which one? So
Oh,
for
the one
for
in
the
the middle.
IJ,
The one in the middle.
the one in the middle.
Yeah.
So I asked you to read it out. So it should be
Inner product of EJ tilde TEJ.
yes. TEI, not EJ.
Okay, EI. Yes.
Yes. And so all of these are inner products in V. Okay, good. So we know what the matrix element is. But now what we want to do is we want to take it and we want to relate it to the inner product of into the matrix element of T, right? So we want to compute this matrix in terms of the previous matrix that we had. So this was what? This was alpha was green and beta was yellow, right? So now you may remember that from the previous formula from before, we had the matrix of T from alpha into beta. This matrix element, so the ith and jth component, this is the inner product of B. This was the inner product in W of T EI, inner product with EJ, inner product with EI. Whoops, this was all in. Wait, I messed up my colors. Yellow was for what? Yellow was for V or for W? Yellow was for W. Ah, so all of these inner products should be.
W.
All of these inner products should be green. No. Yes. Right.
Oh,
No, green is for V, right?
Green is for V. Yeah, exactly. So for V. So
But
since
these are
isn't it
W.
in W?
yes, yeah. There we go. Yes, you're right. That's why it was confused. So these should be in W.
All those are gold.
Yes, sorry. I've confused myself with too many colors. W. There we go. Sorry, and then beta was, yes. And so this is in W. And now this, right, this is also in W. Correct. This is also in W. Good. Do you agree? Okay, so we want to find a way to take this and relate it to this. Do you agree? Okay, so instead of writing this whole thing, actually let's not abbreviate it. Let's just let's abbreviate it. Let's call this, say, Bij, and let's call this, say, Cij. Right, so the matrix forward is Cij, the matrix backward is Bij. Okay. So I want to see how does Bij relate to Cij. Do you agree? Okay, so we're going to write this. Okay, so we're going to write Bij is equal to the inner product of Ej tilde with TEI inner product W. Okay. So now we want to take this and make it look like this, right? So what do we have that's different here? So here, where's the T on this side? Here it's on the right. Here the T is on the left. Thank you. So we want to make this T on the right appear on the left. How do we do that? What can we do? How do we move this to here? Yes. So if you remember from the inner product, it was like skew symmetric. So if you were to flip the entries, then it would be equal to the same thing, but the conjugate. Okay? So I can then write this. This would be,
Wait, could you clarify one thing?
yes.
I'm getting confused because one of them says T E J and the other one says T E I. Like, and that's probably on purpose, but it's just hard to keep track.
Yes, exactly.
What is going
Exactly. Because remember this we originally wrote like this, and it was T star EJ, but then we found out that if it should be EJ inner product TE1, right? So we kind of swapped it using the property of the inner product earlier, right? And yeah, so I'm kind of skipping the step of starting here, then going here. So this is on purpose. You will see it. This is on purpose.
Okay.
We'll see in a moment. Okay. And this was actually the next thing I was going to ask. This is TEI EJ in W, right? This looks very much like this. Do you agree? Just with the indices swapped. Okay, so that's all it is. So then it's just this thing, but instead of CIJ, I'll write CJI. Do you agree? So this is just CJI conjugate. Right? It's the same thing. It's just here it's I, here it's J. So okay, then I just swap I and J to get this. That's it. And now let's look at this equation. So we're saying that the matrix that we're interested in, the matrix of T star, is just CJI conjugate of the matrix of T. Okay, what does it mean when instead of IJ I write JI? What is that?
It means to put the row in the column.
Yes, so that's a transpose. This is a transpose, and this is a conjugate. So I take a conjugate of it. Have people heard of what taking a transpose of a matrix is? Yes?
Swapping rows and columns.
Yes. Well, this. Swapping the indices. Exactly. So, conclusion. The grand conclusion. Oh wow, this is taking longer than I thought. The equals conjugate transpose of T of the matrix from alpha to beta of T. Okay. Now, one of the really important things that we used in this result. What was one of the key assumptions that we had on this? Yes.
The basis is orthonormal.
Yes. So this conclusion only works when alpha and beta are orthonormal. Right? This is another mistake that people often make, is they write down some matrix and say, the matrix for the transpose, is, for the adjoint, is going to be just complex conjugate and transpose. But that is not the case if the matrix wasn't written in an orthonormal basis. So what's important, where alpha and beta are orthonormal. So you have to make sure you have this. So this is important. Okay. So now let's go back to the questions. So we've now answered this one. We've now answered what the matrix is in terms of the matrix of T, it's the conjugate transpose. Okay. Oh, I'm not moved. Good. Now, there's actually one question that we actually didn't. The fact that T star exists isn't obvious, in the sense that so we proved that something exists, but we didn't show that it has the property that if you swapped T star onto the other thing, it has the like defining property of T star. So actually, this is not obvious. This is something we still have to check, right? Because we define some linear map. We define some linear map with this equation, but we haven't checked that it satisfies this equation, right? Okay, so you're going to do that as a suggested exercise. Because this is just like you plug it in and you see it. And in general, it should be obvious that it satisfies this in some sense, like intuitively. Why? Because the way we defined it, we said, okay, let's write down the easy thing and then apply this property and then say, okay, instead of saying that this is equal to this, say this is equal to this, right? And so, in some sense, we've kind of used this property to define the thing, so that property better hold. Though this kind of logic doesn't always work. But in this case, it does. Also, you could really say, okay, using this, you can kind of say that this has to equal to this, and if this has to equal to, if this coefficient has to equal to this coefficient, because the basis has unique coefficient expansions, and because this has to equal to this, then you can, you should be able to deduce this more generally. Okay, but that's
Circular logic, or I feel like you can't just say that that property must hold because we defined it. What if that definition just doesn't work?
what do you mean it doesn't work? I can always define this like this. I can always define this to be equal to this. Sorry, I can always define this to be equal to this.
Yes.
Yes. Okay, but this has to equal to this just by the vectors being orthogonal, right?
Yes.
And then I can say, okay, this coefficient has to equal to this coefficient because the basis vectors here are the same, and by uniqueness of expansion in the basis, this has to be equal to this. Okay, and from that, if you plugged all of that into, if you plug this into here and expanded everything, and then use the fact that this has to equal to this, you'll get that this holds.
Okay.
So I'm telling you how to do the suggested exercise. Okay? Good. So okay, I guess existence isn't immediately obvious actually. And what do we have left? So arguing that T star is unique. Well, okay, I think once you show that the existence property is correct, you can kind of argue backwards that if you work backwards, this is the only thing that can do this. Okay. So do people kind of understand what the adjoint map is, right? So it's something that we have a map going from V to W. It's something that we define that we want to go back such that it plays nicely with inner products, right? Notice that T star doesn't have to be the inverse of T, right? Because we defined T star to be literally from any vector space of any dimension to a vector space of any other dimension. Right? The vector spaces don't have to match dimensions, and you still have a T star. So it's kind of it's not an inverse at all. It's kind of very loose in that sense. But it's something that goes back and plays nicely with the inner products and with T. Okay, I maybe just don't understand this well enough to make a succinct statement about what T star really is. That's okay. I'll have one maybe one day. Okay, so now we will prove the spectral theorem. Okay. So I will write this result here. Okay, I'll write this result here, and I will erase it from there. So okay, for the people on whatever I just copied this equation. Okay, and I will erase everything here. Is it okay if I erase everything here? Was this sufficiently clear? Yes. So now our big result, and we will hopefully prove this big result in like 4 lines. Okay. And so we've kind of managed to speedrun one of the major results that you see in 247 in like the span of 3 days.
We're going to see this in 247.
Everything I told you, you're going to see in 247, all of it.
Okay.
Or at least you should, I think. Or at least I did when I took 247, I don't know. Okay. Spectral theorem.
Is this in 247?
Yes,
Okay.
at least for me. But regardless, you have to know this because it's just everywhere. So let t going from v to v, so it's a linear operator. So a linear operator, and v is of course an inner product space. If t is if t equals to t star, then t has a basis of eigenvectors. So, who knows what an eigenvector is? Okay, good. Basis of, sorry, this is wrong, not eigenvectors, but orthonormal eigenvectors. Or has an orthonormal, has an orthonormal basis of eigenvectors. I'm sorry. Has an orthonormal So okay, let's I've never actually defined what an eigenvector is except for in the problems, I think. So let's write down what this means, you know, for the thousands of fans watching at home. So this means the following. So exists v1 up to vm. So vn. So let's v is finite dimensional. So v is a finite dimensional. This is important. So exists v1 up to vn, such that okay, vi, vj equals 0. The inner product of vi with vj equals 0 for all i's not equal to j. The inner product of vi with vi is 1. And the point, an eigenvector means that tv is equal to lambda v. So applying t to the vector just scales it. Right? So this is what it means to be an eigenvector. Moreover, not only is it an orthonormal basis of eigenvectors, the eigenvalues with eigenvectors with real eigenvalues. Real eigenvalues. And actually, I lied to you. V is not an inner product space. It's an inner product space over C. Sorry, this is really important. This is very important. So this is the spectral theorem, at least in the finite dimensional case. Okay? Do you agree with this? Or disagree? So, orthonormal. I'm missing letters. So what's important is that, okay, so we have a vector space V, it has an inner product on it, and it's over C. So the inner product outputs complex numbers. So V is finite dimensional, and you have some t, and the claim is that suppose t is equal to t star. Okay, so this is an important bit. Why? Before, when we were talking about t star, we had t going from some v to some other w, and t star was going back from that w to v, right? Makes sense? So before it didn't make sense to say that t is equal to t star, because they were linear maps between, from going from one vector space to a different vector space, right? One was going from v to w, the other one was going from w to v, right? However, this one's going from v to v. So t star is going to be going backwards, but from v to v. So both t and t star are linear operators over the same vector space. So, saying that t equals to t star makes sense.
But can't you, if this is just a special case under the regular v to w,
Yes.
so it would
Exactly.
have made sense otherwise too, but
It wouldn't make sense to say t equals to t star if w was some different vector space of different dimension.
actually, yeah.
Maybe I'm just making a point that's not necessary.
No, it does make sense, because you have
Yes.
to take all the domain.
Yes, exactly. I have the domain changes,
Okay.
right? But here the domain is the same as the target, so everything is fine. This makes sense. Okay? And now, before I was always like doing this color coding to differentiate between the inner product on V and the inner product on W. Now the inner product's always on V, right? Because it's very easy. But notice that all the results that we proved before still hold for this, because this is just a special case of that. So this fact about the matrix still holds. And what's important is that now we're going to choose a single basis, and it's going to be a matrix going from alpha to alpha. And the result will still hold. So I'm talking about, this is the wrong camera. Talking about this result. This result will still hold even if t is from v to v, and then we'd want the basis to be, the input and the output basis to be the same. So we'll have alpha alpha, but that still will all work out nicely. And the result that we proved, since we proved it for arbitrary vector space, it will work fine. Okay, so proof. So this is where you have to recall the first set of suggested exercises that everyone did. And on the first set of suggested exercises, there was question 3, which you had to read the solution to, because it was fairly non-trivial. So you should probably read the solution to that. It would be faster, but okay, you can still do it. So from an exercise, we know from exercise that any operator t from v to v, where v is finite dimensional over complex numbers, has an upper triangular matrix. Which means that, so exists basis v1 up to v, so let's put tildes on it for now, v1 up to vn, such that t vi is in the span of v1 up to vi. So why is this called upper triangular? Because if you were to write down the matrix, right? So the input here is v1 up to vn, and the output here is also v1, right? Because this is a linear operator. The linear operator is from a vector space to itself, so you want the input and the output basis to be the same, so you can like multiply matrices. You can multiply the matrix with itself a bunch of times, and the input and output would still make sense. So why is it upper triangular? If TVI is in the span of V1 up to VI, right? This column is TVI, right? The ith column is TVI. And if TVI is in the span of V1 up to VI, that means it only has entries non-zero entries kind of above here, and everything below has to be 0. Do you agree? If TVI is in the span of V1 up to VI, then VI plus then the component in front of VI plus 1 is 0. Right? And so everything below the ith row is 0.
Why did you write V with tildes for the basis?
Oh, right. There should be, because we're going to later.
They all have
They all have tildes because later we're gonna define a different basis. Like this is not the final basis that we're gonna have in the end. We're gonna do stuff to this basis, massage it, and then get the basis we want. Okay. So this is a fact that we did in the exercises, that for any operator over a finite dimensional vector space V, which is over the complex numbers, any operator has a matrix has a basis in which the matrix is upper triangular. So there exist these V1 up to Vn tilde, such that T Vi is in the span of V1 up to Vi. And this condition is exactly the same as saying that the matrix is upper triangular, because everything below this diagonal will be 0. Do we see why this implies that everything below the diagonal is 0? If you don't, please let me know. Yes? Okay, everyone's good. So I'll erase this drawing of a matrix for now. Okay, so, okay. However, so for the people who actually did this question, what is not necessarily true about this basis? What were we talking about so far for the previous hour?
It's not orthonormal.
Yes, we're talking about like the inner product and orthonormality and stuff. This is true for just any finite dimensional vector space over C. It doesn't even need an inner product. So this might not be orthonormal, right? We want an orthonormal basis. So if I give you a basis, do you agree? If I give you a basis, what can I do to it?
Replace vectors in it.
Yes, but so last time we talked about a certain kind of thing, and then it was on the exercise 2, where you think, or something, on the suggested exercises.
I can't remember the name, but you can.
Remember, we can do, if I give you a basis, I can always turn it into an orthonormal one. Why? How do I do it? I take the first vector, okay, I just normalize it and have it length 1. Then I look at the second vector and subtract the kind of bit from the first vector from the second vector and normalize that. And have that to be my second vector. And this was called the Gram-Schmidt procedure. Remember? We were kind of looking at two vectors. The like inspiration was that, you know, say you have one vector and then some other vector, right? And then you take this one, you would make it orthonormal, right? Then you'd look at this vector, remove kind of the vertical component from it, remove the vertical, you'd remove the component parallel to E1, and you'd just be left with this vector, and then normalize this vector, and then your basis would now be this vector and this vector, and they'd be perpendicular to each other. Right, so the idea was to start with vectors, start with a vector, and move to the next vector, and remove the component parallel to all the previous vectors, and you will be hopefully left with something orthonormal.
Did we do that using the V is equal to all the coefficients being the inner products times the E's?
We didn't do that using that because we started off with, because this was just some basis. It wasn't necessarily necessarily orthonormal. The coefficients being equal, that is only for an orthonormal basis. Yes. So this is, I explicitly defined what the, if I make a new basis out of the old one, what the EI vector would be. We just explicitly defined it as a formula, and then on the homework suggested exercises, you just proved that those would be the orthonormal vectors. Okay. So by Gram-Schmidt, so we can apply Gram-Schmidt, and we did this last time. Gram-Schmidt, you have the following. Can construct orthonormal basis V1 up to Vn such that Vi is in the span of V1 tilde up to Vi tilde. So this is something I can construct. So by the Gram-Schmidt procedure that we discussed last time, you should hopefully review. It's very important. So it's kind of, we had one theorem that told me I have a basis in which it's upper triangular. And then I said, okay, by using this Gram-Schmidt procedure, I can transform this basis into another basis. And in fact, we're going to check in a moment, convince ourselves that in this new basis, the matrix will still be upper triangular. So it turns out that we just proved that over the complex, over for an inner product space, finite dimensional over C, any linear operator has an orthonormal basis in which it's upper triangular.
I have a question.
Yes.
What does it mean over C? Why do we need to say that?
Because this theorem holds only for V over C.
Oh.
Yes. This theorem, you need V to be over C because you need, like, the thing that's important about C is that any polynomial has always a root. So you can factor any
I was
polynomial.
thinking it might have to do that.
Yes, and that's kind of how we prove this theorem.
Oh, okay.
So you should, it's a really fun proof. You should, read the, I posted the solution. Yes. But it was also a tutorial problem in 240. I think a bonus one. Yes. Okay. Now, how do we convince ourselves that in this new basis the matrix is still upper triangular? Well, so if Vi is in the span of V1 up to Vi, of the old Vi's, then TVI, right, can be written as some linear combination AI of T of the old VI's. Do you agree? The sum over J. Right? Do you agree? But each of the TVJ's, and this is J equals 1 to I, but this has to be in the span of V1 up to Vi old, which is equal to the span of V1 up to Vi. And yes, so now the matrix is still upper triangular. So we wrote down a new basis, which is orthonormal, and the matrix is still upper triangular in this basis. Okay? So let's call this basis, say alpha twiddle, and this basis alpha, and so the claim is that the matrix in this alpha is still upper triangular. But now all the VI's are also orthonormal, right? So we picked up an extra condition. Do you agree? Now my claim is alpha is in fact the basis that we always wanted. So 3, conclude the result. So there's 2 steps. That's it. And we've now constructed the basis. So 3, alpha equal to V1 up to Vn is this basis. That we so want. Okay. How are we going to prove this?
Wait, I have a question.
Yes.
I missed something. Why is the span of those two equal?
Because the Gram-Schmidt procedure was such that I take these V1s up to V1s, Vn's, the tilde ones, the old ones, and I use them to construct the new VI's with the specific property that Vi is in the span, so that you can construct it with this property, that the new vectors in the new basis have the property that the ith newest one is in the span of the first I, old ones, right? Okay, so if this is true, then TVI has to be equal to, by just linearity,
Yes.
AJT V tilde, the old VJs, right? And this is a sum from J equals 1 to I. Do you agree? Now, in the old basis, we assume that TVI was in the span of V1 up to VI. So since I'm only adding up vectors from TV1 to TVI, then all of these have to be in the span of V1 to VI because the old basis was upper triangle, right? But we constructed the VIs such that the span of this is equal to the span of this. We just
Wait, isn't one of them? But okay, I understand that the span of the
So you don't understand this stuff?
tildes- Yeah.
This is we constructed the new VIs for this to be true. Like they were constructed with this property in mind.
Okay, I understand that the I think the ones without the tilde,
Yeah.
that span, I see why that one would be bigger than the other one. But
What do you mean bigger? It wouldn't be bigger. It would be
Because
exact the same.
Because each VI is it not? It is inside the span.
Yeah, it's inside the span. So I can write this one as a linear combination of the other ones,
Okay.
right?
Yes.
So then what's the question?
I don't really know. It's okay.
It's okay, but
Yeah.
you believe that this is true. Maybe.
No,
No, why? Why not?
I don't know. I'm
You know,
confused by
if
the
one
reason.
vector is in the, it's just I just did a change of basis. You know, this is a basis, and then this is also a basis for the same space, and I just did a change of basis,
Okay.
right? Where this basis is much nicer than this one. Okay. So now, I am claiming that we're done, and this is the basis we want. How do we see this? So why did we want to write down an orthonormal basis? Why did we want to write everything down in an orthonormal basis? So we can use all the stuff that we just proved before. Do you agree? Because everything we proved before was in an orthonormal basis. So what did we have? What was so special about T? The special thing about T, which we still haven't used, is that T is equal to T star. Do you agree? So let's use this fact. So we know that the matrix from alpha to alpha of T, right? This has to equal to, well, T is equal to T star, so this has to equal to the matrix from alpha to alpha of T star, right? Because T is equal to T star, they're the same operator, their matrices have to be the same, right?
Sorry.
So T is equal to T star, therefore this is
yes,
true.
Yes. Should there be twiddles on this? Or no?
No,
Okay. Yes.
right? However, before we proved that actually the matrix should be the conjugate transpose. If for T, if I'm writing the matrix of T star, that always has to be the conjugate transpose matrix of the matrix of T. And actually, this is something that we write as dagger. Not a T, but a dagger. Well, this looks like a T. You write it as a dagger.
That looks like a cross.
Yeah. Well, across a dagger, it doesn't matter.
Is that supposed to be like a straight vertical line?
This is
Okay.
this is a bracket.
Okay.
So this is conjugate transpose. Dagger means conjugate transpose. Okay? But now, let's imagine how this looks like geometrically. Like just look at this matrix. Imagine this matrix, right? So what did we know about the first matrix? What was the first matrix? The first matrix was, what was the special nice property about it? So this matrix, alpha to alpha of T. What was so nice about it?
Triangle.
Upper triangular, right? So how did this matrix look like? It looked like this, and it had stuff up here. Do you agree? Yes. Now, the matrix for T star is the same matrix, right? Do you agree? However, we also know that the matrix for T star has to be the conjugate transpose of the same thing. How do you do the conjugate transpose? You reflect all the values in this axis, right? In the kind of diagonal, you reflect everything in the diagonal, and you take conjugates of all the values. Do you agree? So you get that this has to equal to 0 here and stuff here. Do you agree?
Wait, is that what it means when you write a conjugate bar over the whole?
Yes,
Oh,
I mean
yeah,
every
for
entry
each
is conjugated.
individual element. Okay,
Yes.
that makes sense.
Yeah, that's a good question. You didn't say it. Okay. So if this has to equal to this, right? What does it tell me about the stuff here above the diagonal? It all has to be 0, right? Because, well, if this has to be equal to this, then this has to be 0, this has to be 0. So what's the only thing that's non-zero? The diagonal. So we get that in this basis, the matrix must be diagonal. So this is kind of 3 continued. Therefore, matrix is diagonal. Okay. But if the matrix is diagonal, what does that mean? That means that TVI is equal to some number times VI. So that's exactly a basis of eigenvectors. Good. Now this is also an orthonormal basis of eigenvectors, because we said that in step 2 by Graham-Schmidt we chose V1 up to Vn to be orthonormal. Yes.
Why is TVI equal to some multiple times VI?
Because so do you agree that this matrix has to be diagonal?
Yes.
Okay. If the matrix is diagonal, that means that the only non-zero coefficients are CII. So if you expand TEI,
Yes.
then it's going to be 0, 0, 0, CIIEI, 0, 0, 0, 0, 0.
Yes.
Okay, so that means TI has to be equal to CIIEI.
Yes.
And then in fact the eigenvalue is CII. Do you agree?
Yes.
Okay. So this implies TEI is equal to CIIEI. So this is what it means to be upper triangle. Okay. But what do we know about CII? We still have not used one thing. CII, when we took this transpose, we also took a conjugate. Do you agree? But this means that the CII has to equal to CII conjugate. Right? Because the stuff on the diagonal stayed on the diagonal. Therefore, CII has to be real. Okay, so see, we proved this very powerful theorem. The fact that a self-adjoint operator, I didn't say that this is called self-adjoint, we'll define this to be called self-adjoint in a second, has an orthonormal basis of eigenvectors with real eigenvalues. Okay? Do people see this proof? So, if you have any linear operator over an inner product space that's over C, and this operator has the cool fact that T equals to T star, that means that there has to be a basis of an orthonormal basis of eigenvectors with real eigenvalues.
So there is always an orthonormal basis.
So in general, for any operator, there's always an orthonormal basis in which the matrix is upper triangular.
Okay.
But if T is equal to T star, then you can make this argument and realize that in the case that T equals to T star, then that base is in fact diagonal, not just upper triangular.
Did the Graham-Schmidt construction procedure, did that say something about upper triangularity?
Yes, that had this condition. That had that V1 up to VI was V1 tilde up to VI tilde, and that kind of gave us the upper triangularity. That it preserves upper triangularity. If the matrix was upper triangular before, it still is upper triangular now. Okay. So I kind of didn't write this out very clearly. I just gave you like a picture of like, you conjugate transpose it. But okay, if you were to write out all the matrix coefficients as like Cij and write out the matrix multiplication and so show that this has to be equal to this and this has to be equal to 0 and whatnot, okay, you'll arrive at the same result. But this is like, I feel like more clear of how to like see why this works. Okay. And now we're ready for quantum mechanics.
Okay.
Now you know, like, practically all the math you need to know for, like, most undergraduate quantum mechanics, with the exception of, so far we've been talking about, like, finite dimensional vector spaces. We need to try and extend this stuff for, like, infinite dimensional vector spaces. But I'll be, like, a little less rigorous there. I'll be like, yeah, it works. For the most part.
Why is this thing called the spectral theorem?
Good question. Well, because it tells you something about the spectrum of this operator. So the there's kind of a physics definition. Well, it's really very funny because, so the definition, the spectral theorem, the word spectrum, I haven't defined what the spectrum is, but the spectrum is like the eigenvalues plus some other things. And the spectrum was a definition independently, I think, introduced by Hilbert. He defined what the spectrum of an operator is. And then quantum mechanics came around, and it turns out that in quantum mechanics you have some operators called observables, and their eigenvalues, so some parts of their spectrum, can, for example, give you like the energy, like the Hamiltonian is some self-adjoint operator, and it gives you its eigenvalues give you the possible energies of the system. So that's like the spectrum, because if you were to look at like the lines in a hydrogen atom, right? You know how you have like the lines of colors that it emits,
Yeah.
right? That's kind of like the energy level, related to the energy levels. And so that's like the spectrum. So that's kind of the physics intuition for it. And why Hilbert called it the spectrum and the spectral theorem, I don't know. He just got real lucky with it, because he did this before quantum mechanics. So actually, let's do like one more definition to tidy things up, and then we're done. Okay, one more definition. I will erase this and write the definition here. So let V an inner product space. Let T be an operator on V, a linear operator on V. That's what this means, linear operator on V. So a definition, T is called, you can't. Sorry, I keep forgetting to move the camera. T is called self-adjoint or Hermitian. Actually, maybe there's something else for Hermitian. Maybe I'm lying. That's okay. If T is equal to T star. So, this condition that we had in the spectral theorem, I'm calling this self-adjoint. Why? Because it itself is equal to its own adjoint. Therefore, it's self-adjoint.
I have a question.
Yes.
If T has an orthonormal basis of eigenvectors with real eigenvalues, that does not imply that T equals to T star?
Oh, it does.
Okay, so that's an
So
if
this
and
is
only if.
correct.
Oh god.
This is in fact an if and only if. Why? Because
Oh yeah.
Because if you know that the if you know that the basis is orthonormal and the matrix is diagonal, then you know that the matrix has to be equal to the conjugate transpose. You take the conjugate transpose, you realize the matrix is still the same because it's diagonal. It only has real numbers. Oh, so then the matrix has to be, it satisfies this property. Therefore, it's equal to the adjoint. So this is in fact an if and only if. Good catch. I should have said this. So now we can actually rewrite this theorem. So this theorem can be rewritten as a self-adjoint operator over V which is over C has an orthonormal basis of eigenvectors with real eigenvalues. Okay, so this is another way to rewrite the spectral theorem now that we have all the definitions. Okay. Perfect, it's 8:01.
Crazy.
I said we'll end early today, and we did.
Sure.
Because we started 10 minutes late.
Minus 1 minute.
Right? We started 10 minutes later, so really we just ended 10 minutes earlier.
9.
Pardon?
9 minutes.
9. Okay. Wait, there's 1, 2, 3, 4, 5, 6, 7 of you. And, okay. So you guys have not done this in 247, any
No,
of it.
not
Have you
even.
talked about inner products?
No.
247?
We just started talking about minimal polynomial.
Okay, in that case, it's really good that this reading group exists. And I will stop the recording.